All right, hello everyone. Welcome to the 2022 ACOM seminar series, and thanks again for working with us for a last-minute solution here and attending virtually. It's an honor and a pleasure for me to introduce Dr. Prasad Kasibhatla. He's a professor of environmental chemistry at the Nicholas School of the Environment at Duke University. Prasad graduated with a bachelor's degree in chemical engineering from the University of Mumbai and received his master's and doctoral degrees in chemical engineering from the University of Kentucky. He joined Duke in 1997, and his past research has focused on understanding natural and anthropogenic impacts on the chemical composition of the atmosphere using models in conjunction with remote and in situ atmospheric chemical measurements. His current research focuses on elucidating the role of aerosol transmission in shaping large-scale COVID-19 disease dynamics and on characterizing the collective impact of micro-scale mitigation strategies like ventilation and masking on macro-scale disease dynamics. Today, he's going to tell us about the heterogeneity in airborne transmission of COVID-19 by respiratory aerosols. Before starting and handing it over, I'd like to remind you can either enter your questions in the space below the video at any time during the talk through Slido. And at the end of the presentation, we'll read those questions to Prasad. So Prasad, please take it away.
Can somebody start my video? I feel it says I can't start it. Thank you. Thank you all again. Thank you, everyone. I really appreciate the invitation. I'm glad to talk to you about some of my work. So I'm going to talk about heterogeneity in airborne transmission. I'll talk about what heterogeneity means, what transmission by respiratory aerosol means. And this work, I've been collaborating with a number of people, including people like Jose Menes and Zipeng at University of Colorado, Chris Kappa at University of California, a bunch of others. So I'm going to get started. So first of all, let me just kind of step back and give a big picture perspective where we are in terms of the COVID pandemic. These numbers are from the WHO coronavirus, start my pointer here. Dashboard, the WHO dashboard as of last week. You can see that numbers seem to have gone down, but part of this might be testing. These are number of confirmed cases. There's about 530 million or so. There are some estimates that there are about probably 6 times as many cases or cumulatively since the start of the pandemic as this number reports. And the number of deaths is about 6.3 million, though again, there are estimates that the number of deaths from COVID is probably about 3 times higher or so. So, major pandemic, obviously. There's a number of studies going on trying to understand various aspects of it, both to understand what happened, to prepare for the next pandemic, and to understand, I think, how respiratory diseases, the dynamics of respiratory diseases, if you will, for the future. So how did I get into this? I got into this sometime a couple of years ago, late spring 2020, early summer 2020. At Duke, we were asked to consider whether we would teach online or in person in the fall of 2020. I started thinking about it. Right then, there were some papers that came out. This was Prather, for example, in Science 2020, talking about airborne transmission by respiratory aerosols. So I started thinking I can calculate my risk before I make a decision. I started doing some back-of-the-envelope calculations, doing some Google searches, and I came across, obviously, this calculator many people might have heard of that Jose Menes' group put together. It's a pretty simple spreadsheet model that kind of gives you for various situations what your risk is. I started thinking about this, and I worked with Jose. Jose's model kind of gives you a point estimate of risk, but risk actually varies based on a number of circumstances. So we came up with the Monte Carlo version of this that gives you kind of a range of risks and then a best estimates of risk. And this was working with Jose. So that's when I kind of first started getting into this. Just a brief aside, here's my ACOM connection to this work. When I was working with Jose about this, Alma Hodzik, I was communicating with her about something. She was interested in this. And at that point, I had created this spreadsheet-based, this web-based version as a spreadsheet, just like Jose did. And I've been communicating with Alma, and Alma sent this email. You can see this was in July 2020 to me and Jose. And she said, why not build on this, making a web HTML calculator, which is exactly what we did. And she also, at that point, suggested that, is there a way to account for distancing between people? And towards the latter part of my talk, I'll come back to that. So this is my ACOM connection to this work. So I should thank Alma for these suggestions. Okay, so respiratory aerosols. So it turns out that when we breathe, when we talk, when we sing, when we cough, we emit a lot of aerosols, tiny respiratory aerosols. Various processes, it is because of vibration in the larynx, for example, with fluid film formation and rupture. When your mouth and lips move, there are these films that form. You breathe, air pushes against it, they rupture, you form little respiratory aerosols. Down in the lower down in the respiratory system, you have high-speed airflow over mucosalivary fluid, creates instabilities, and these waves, essentially it's a wave-breaking process. And down in the bronchial regions and alveolar regions, during exhalation and inhalation, there are these film barriers that form and then burst. So there's a number of ways in which human beings, when we breathe, when we talk, when we sing, we emit these aerosols and larger droplets. And just to give you some perspective, the coronavirus, the size of the virus is about 0.1 micron or so. When we are breathing, talking, singing, we put out a number of different sizes, less than 5 micron, 5 to 100 micron, greater than 100 micron. These are some good, useful classifications. When you put out these aerosols, they typically evaporate down to about 25% of their size. So something like 100 micron aerosol, when emitted, will evaporate down to 20 or 25 micron pretty quickly, stays afloat depending on the lifetime of that droplet. So if you think about deposition lifetimes, particles that kind of end up below 5 microns, so dry, that is less than 20 microns or so hydrated, stay afloat for quite a long time. Particles that are kind of in the 5 to 20 micron dry size stay afloat for some time, not as long as the other ones. And the larger droplets fall quickly to the ground. So it's these probably, and a lot of the virus is being found in these aerosols that are less than 5 microns when they're dry, so about 20 microns when they're emitted. That's kind of the size range of interest, if you will. And there's the conventional wisdom was that the way you're getting infected is these larger droplets that are spraying on your face or spraying on surfaces that then you touch and you transfer the virus to your surface. I think there's some pretty compelling evidence that a major and probably a dominant route of transport of transmission is aerosols. And there's this paper by Tricia Greenlaw and a bunch of others, and they point out 10 reasons that support airborne transmission as opposed to transmission through these spray-borne droplets. So the idea is that you're really inhaling these aerosols that contain this virus, as opposed to being sprayed by them, or as opposed to touching contaminated surfaces with your hands and then transferring it to your mucous membranes. And so based on that, there have been a number of people who have come up with these models that calculate what I call event-specific risk of transmission. So this is, for example, our web sheet calculator. This is a table from a recent paper by Enrique and all. And what they've done is they've calculated your risk at various confidence intervals for a shared office, for a classroom, the baseline conditions with windows open, things like that. So there's a number of studies like that that have looked at what I call event-based risk. If you're in this classroom, if you're about what's the risk of transmission and how does it change with mitigation measures? So that's kind of this event-specific thing. At the other end of the spectrum, epidemiologists have been studying the large-scale epidemiological characteristics of the disease. One of the ways in which we characterize this is something called R. And R is, you can think of it as the number of people, secondary cases, that an index case, one person is infected, how many people do you transmit it to? And the average early on was about 3, that is, each person transmits to about 3. Now, with Omicron, it's probably higher, more of the order of 6 to 8. And in terms of mitigation measures, once you put mitigation measures in place, if you can drive that number below 1, then each person is infecting less than 1, and over time, the pandemic will die down. That's one aspect, but it turns out there's another key aspect of it, and that is something called overdispersion. So what happens is you have a person infecting somebody. Some of those people who you infect might not infect anybody else. Some might infect a couple of people. Others here might infect more than one person. So you have a heterogeneity in transmission. That is, there are some people who can transmit to a number of people, others who transmit to one or maybe no one. Okay? And this is also related to something called superspreading. And this has been something that has been observed throughout the pandemic. This is one example. You find these clusters of cases associated with superspreading events. This, for example, is a contact tracing study that was published in 2020. It was called the bar and band study in Hong Kong, a cluster of cases linked to a single bar in which there were 73 primary cases. That is, there were 73 cases associated with events in that bar. Those in turn led to another 33 secondary, tertiary cases, etc. They never traced the original person, but it's believed that an individual was responsible for this large cluster. Similarly, Shelley Miller and colleagues had this seminal paper in Indoor Air in 2020, where they looked at this Skagit Valley corral. This was a case where there was a corral practice, and 61 attendees. There was one infected person. The infected person, we call that the index case. The index case infected 53 people. And this was one of the papers that kind of laid the foundation for us thinking about this as the super spreading events driven by aerosol transmission. And that's related to what's called overdispersion. Overdispersion refers to the fact that a small number of index cases, in fact, if you contribute the most to secondary cases. This was an analysis published by some epidemiologists looking at outbreak sizes and transmission patterns. And they concluded that for this range, which was typical, a person infecting 2 to 3 people, a y-axis is the number of people responsible for 80% of the transmission. Somewhere between 10 and 20% of index cases are responsible for 80% of secondary cases. So a lot of people infecting very few people, some people infecting a lot of people, leading to these super spreading events. There have been large-scale epidemiological modeling studies where they basically divide people into susceptible, exposed, infected, and recovered. You have these pools of people. There's dynamics that people move between these pools. You can overlay on the network models. I'm not going to go through the details of this, but down here, what's important is that even in this, what they find is that 90% of the infections are happening in about 10% of what they called in this paper POIs, which is places of interest. So they looked at restaurants, bars, retail, things like that. And in their modeling analysis that was fitted to real data, they found that a small fraction of events led to most of the transmission. So very consistent story from epidemiology. And so my question has been, is airborne transmission by respiratory aerosols consistent with what we see at the population level? And the work I'm going to talk about today is an offshoot of a work we just published in Physics of Fluid, where we looked at this issue, but we looked at it very narrowly from the perspective of restaurants in a narrow time window at a single point in time. And what I'm going to do today is talk about this over the lifetime, over the illness lifetime of a person. Okay. So here are my questions that I'm going to look at. Is aerosol transmission consistent with observed heterogeneity? That is over dispersion. At a population level, can aerosol transmission explain that? And if so, what is it that controls it? And what are the implications for intervention? So those are the questions that I'll address today. And to do that, I use a model. It's a pretty straightforward box model. There's an index case. They're emitting aerosols. They have virus in it. There are susceptible people in it. They breathe the aerosol. The amount they breathe depends on the concentration in the space. The concentration in the space depends on the emission rate, mask exhalation efficiency, how things decay, what the ventilation rate is, what the room volume is, the deposition rates, the breathing rates. And I'm going to think about how much infectious aerosol is this person emitting and how much do they end up breathing. And I'm going to use the term virion here to refer to the infectious form of the virus. You can measure RNA copies in your swabs and stuff, but not all of that RNA copies that you're measuring is infectious. I'll refer to the infectious part as a virion in this talk. So you can use a simple box model, and if you know these various parameters, you can calculate concentrations, how much is inhaled, and we use a dose response curve that is based on some human challenge trials. The challenging thing is, how do you specify all of these variables at a population level, including near field interaction? How do you specify the distributions, if you will, of how much people are emitting, how long people are seeing each other, what the ventilation rates are? And that's what I'm going to spend quite a bit of my talk explaining how I do that. So my approach here is what I call a pseudo-population analysis. There's a lot of these things that we don't know the details of, but we try to make informed guesses on the distribution of these things. And so I call this a pseudo-population analysis. I'm going to do some Monte Carlo calculations with randomized input variables. And I'm going to follow 10,000 index cases over 12 days of infection. Okay. So first thing, Virion emissions. How much infectious virus are people emitting in respiratory aerosols? There's a wide range of this for a variety of reasons. And so I'm going to talk about that first. How do I do that? I model that as how much respiratory aerosol we're putting out and how much viral load is there in our body. And it's some function of that. And I'm going to talk about these two terms now, how I model virion emissions. So first of all, respiratory volume emissions. This is, I based it on Chris Kappa's work. They have an APS instrument. They have people breathe and talk into it. And they measure the number of particles that people emit, different participants here, and the size distributions of the particles. You see that different people emit different amounts, reading the same passage. Size distribution, it varies with how loud you're speaking. The number of particles varies with how loud you're speaking, but the size distribution is roughly the same. So I use these APS measurements to prescribe a PDF of how many particles people are emitting. We correct this for the APS sampling rate compared to your airflow exhalation rate. I restrict it to less than 5 micron dry because that's where we're finding the virus. I assume that everybody is speaking at intermediate loudness in my pseudo analysis, and that the activity they're doing is either sitting, standing, or some light activity. Randomly, they're assigned an activity. And the reason activity is important is because your exhalation rate and inhalation rate vary by a factor of 3, going from about sitting to light activity. Okay. And I assume that the index case in this place is talking for somewhere between 5 to 25% of the duration of the event. And I'll show you why in a minute why this is an important issue. So here is a PDF of the hydrated volume emission rate, and this x-axis is log 10 nanoliters per second. So this is the PDF. Breathing, people are emitting somewhere between 10 to the minus 3 to 10 to the minus 6 nanoliters per second in aerosol volume. Talking is about 2 to 3 orders of magnitude more, 10 to the minus 2 to 10 to the 4. So if I combine these two with my random distribution of how much people are talking, this is what I get for the distribution. Somewhere between 0.01 to 10 to the minus 5 nanoliters per second. Okay? And that's an important number to remember. So we're putting out something much less than 1 nanoliter per second. when we're talking and when we're breathing. So that's kind of this first part of this equation. The second part is this, how much it depends on viral load. Okay, this is the second part of the equation I want to talk about. So viral loads vary from person to person, and what's shown here is data from a number of individuals. This was a paper published by Key et al. In Nature Microbiology. They followed infected individuals over time. And what's plotted here is, this is something called a CT value, which is a cycle threshold value. The lower it is, the higher the viral load. People start off at a low viral load, they go up and then come down. The dots here are samples from saliva, samples from nasal swabs, and the lines here are lines from the in-host viral dynamics model fitted to the data. So they have calibrated essentially a viral dynamics model that calculates how the virus replicates within the human body using data that they have sampled from individuals. Okay. The viral load data is representative of alpha and pre-alpha, so it's important to understand that my analysis really refers to that. So I contacted the authors of these studies and I said, from your model, can you generate for me viral load evolution in time for 10,000 virtual individuals, my 10,000 index cases? And they did that, and that's what I used to drive my model. So for these 10,000 virtual individuals, I have daily viral loads that vary from day to day. And each person, some people go to a higher viral load, some go to lower, but this is the general pattern. So that's viral load, but the virions, which is what we're interested in, is what fraction is infectious. I model it as some constant with and then a proportionality factor, an exponent to the viral load. Almost all aerosol models assume that infectious virions are directly proportional to the viral load. The amount of infectious virions are directly proportional to the viral load. But it turns out that if you look at cell culture data, that's not true. That at higher viral load, there seems to be a saturation effect, that it can be captured by power law dependence. So in my model, I assume that the infectious virions is proportional to the proportionality factor, the viral load, which comes from the in-host viral dynamics model, raised to an exponent. The mean of the exponent is 0.6, but I choose a random distribution from 0.5 to 0.75. Okay? And that's based on the cell culture work that has been done. And I have a proportionality factor that I'll come to in terms of how I specify it. And I run my model both for the linear case and for this nonlinear case, where this exponent h here is sampled from a uniform distribution between 0.5 to 0.75. And so that's how I model Virion emissions. Okay. The next thing is, how many people are you meeting? How often are you meeting them, each index case? For that, I use a PDF that is derived from some work done by Goel et al., where they fitted a statistical model to outbreaks, to time series of cases. And so they in their model, they use a gamma distribution, they derive the parameters of their distribution, and I essentially use that. So I have 10,000 people, 12 days, 120,000 events. And in each event, I pick from this PDF in terms of how many people you're meeting. So I'm assuming that each index case meets all their assigned contacts in each day at one event. So obviously idealized, that's not what happens in reality. You might meet some people once, and then later on in the day, you'll meet some other people. So this is highly idealized. I also assume that the event duration is somewhere between 15 minutes to 3 hours. And again, I use a kind of a log normal distribution with a median that's a little over half an hour or so. So each index case is meeting their entire contacts for that day in one event that lasts for somewhere between 15 minutes to 3 hours. Again, it's randomly assigned. Next is what's the space volume they're meeting in, because that determines the dilution. For that, I assume that based on these American Society of Heating and Air Conditioning, the ventilation, who set the ventilation standards, their default occupancy densities, they range roughly from 1 meter square to 10 meters square per person. I assume it's a uniform distribution. Then if you flip it, it becomes a distribution that looks like this. So I have about 120,000 events. There's a log scale. Most events, it's not very crowded. There's about 10 to 20 people per 100 square meters. While there's a few events which are very crowded, there's one person per 100 people per 100 square meters. And once I know the density per meter square and I assume a height, I can calculate the room volume. This is what it looks like. Ventilation and filtration, this depends on how this will determine how much you dilute the virus. There are measurements from office buildings. I use that, and essentially it's a log normal distribution. Most places have about air changes, so it's about 1 air change per hour. So from a chemistry perspective, think of it as an e-folding lifetime due to ventilation of 1 hour. Okay. But there's some places that are better ventilated. If you take this and convert it to a volumetric ventilation rate, turns out about 2 to 3 liters per second per person. And just canonically, infection control recommendations are 6 air changes per hour or 10 or 10 liters per second per person. And I'll come back to that at the end. And finally, how are people interacting in the space? There's near field interactions. What happens when you're in the near field is if you're in the far field, you're essentially breathing in air that's been mixed through the room. If you're in the near field, you're breathing in this respiratory jet that's being diluted by entraining air from the background here. This is a conceptual model from Lee et al. I assume 2 cases. One, I assume that I assume in all cases that there's an infector that a susceptible person is at a reference distance of 1.5 meter from an index case. They're breathing in this air. I assume 2 cases, a dilution factor where this air is diluted compared to when it's coming out of the mouth by a factor of 24 from the background air based on Lee et al. And Jose Jimenez said they've done some measurements using CO2 and they estimate that the near field dilution is actually higher. So I diluted by a factor of 240. This is what I call my 240 case. So a subset of people in that room are getting near the index case, the infected person. I assume it's somewhere between 0 to 20% of them. And so they spend some portion of their time near the person and some in the background. The rest of the people spend all their time in the background. So this is basically my world. In my world, each index case is meeting their assigned contacts in a room. Some of them they're meeting close by for some time and far away, dispersed in the room other time. Other people they're meeting undispersed. They have randomly assigned room volume, room ventilation, how many people and stuff. So that's my pseudo world. Okay. And I do 6 base case simulations. Two because I do 2 different cases of this exponent, and I do 3 cases of interactions, one where they're in the well-mixed room, one where the dilution factor is 240, but some of them are in the near field for some of the time, and one where the dilution factor is 24. 6 base case simulations, and this is my parameter phi now. In each case, I tune this parameter to get an R of 3. That is, each index case is on average infecting 3 people over the course of their illness. So that's how I do my modeling. So that's my setup. Here are my results. I'll start with these results here. So the first thing is this overdispersion. What I show here is my 6 cases. It turns out that the well-mixed case, the WM here, is right on the near field 240 case. So in the case where you're diluting the near field by a factor of about 240 relative to with the background air. So 239 parts of the background air, 1 part of the air coming at the concentration coming directly from your mouth. It's indistinguishable from a well-mixed model calculation. Okay? So I'm not going to show the well-mixed anymore till the end. The dashed lines show the cases for H is equal to 1, and the solid lines show it for the H being variable, the exponent. So there's no difference between the well-mixed and the high near-field dilution rate. But if you look at these two cases with the exponent H is 0.5 to 0.75, you see that 80% of the infections are caused by about 20% of the people. Okay? And that's right in line with these observations. That 10 to 20% of the index cases give 80% of the secondary cases. So in my pseudo world, I've assigned people to these random places. I've tuned the model so that I can get the same, each person infects 3 on average, but this is an emergent property from the model. There's nothing tuned here. It just turns out that in the model, the output from the model shows that you capture this observed over-dispersion very well. So this observed constraint is being captured by this model. There's another observed constraint, and this was work that Zi Peng and Jose Menes and others did. What they did was they looked at 12 reported outbreaks, which are shown in these crosses here. Okay. And the probability of infection in each case they had. They also, for these 12 cases that were studied, these case studies, they had data on how much people were talking, how much people were, what was the volume of the room, how long they were meeting for, what the ventilation for. They combined all of those into what they called a relative risk parameter. And that relative risk parameter accounts for how transient it was, did things build up to steady state, what was the type of physical activity, because that determines your exhalation rates, what was the type of vocalization here, was there mass cues, how long was the event, what was the volume of the room, and what was the air change rates. They combined all of this into what they called a risk parameter. So you can think of this risk parameter that is determined by the characteristics of the event, not by the characteristics of the index case viral load. Okay? And so these are things that you can control. So, and they found this really nice relationship. This is based on the observed data, the solid line. And because each of their parameters, they had measurements, but it was not, they had the measurements were uncertain. These were their 95% confidence limits on their estimates. And so the question is, can my model reproduce this? So I'm going to show only the H is equal to 0.5 and 0.75 cases with the NF 240. This is the high near field dilution and the low near field dilution. And at first glance, it doesn't appear to be really good. There's a number of points here where the risk parameter is high, but the infection probability is low. That is not seen in their 12 outbreak studies. Okay? So this is looking at all events. But if I look at events where there are actually infections, it looks a lot better. You get rid of some of these. And you see now that these blue dots and these red dots, each of these dots represents one of 120,000 events. Okay. You see that they fall kind of roughly along these lines, except that the variance is higher. So the reason that is that Z and Peng and Jimenez and Jose and all considered only variability due to variability in vocalization and the room size and the duration of the event. It turns out that this other extra variability is because of variability in terms of how much viral load the index case has, as well as that exponent in terms of how much infectious virons there is. So there's a reporting bias that affects all events. So because I'm simulating all events, I have a number of events where nobody's infected. Obviously, those are not reported when people are talking about outbreaks. So there's that bias. But nevertheless, it's pretty clear that there's variability in infection probability beyond what can be explained only on the basis of this hazard parameter. So I would argue that it's the combination of the hazard parameter variability, how risky the event is in terms of duration, and what the vocalization activity is, in addition to variability in viral load that controls your infection risk. So in fact, if I fit a curve like they did, my curve would fit right on theirs, except my variance is higher. So again, consistent, broadly consistent with what is being observed. Okay. But here's the kicker, and here's, I think, what the kicker is when it comes to aerosol transmission. This is a complicated slide, so I'll explain it to you. So what I can do in my model is once I calculate the virions per milliliter of aerosol, I can compare it to the viral load. So for each case, what I plotted here is the amount of infectious aerosol in RNA copies per milliliter of the aerosol divided by the RNA copies of total virus per milliliter in the respiratory fluid. So infectious virus in aerosols per milliliter, total RNA copies per milliliter in the fluid. For the linear case, obviously, if when I calculate it out, it's just a constant. The concentration of infectious virus in the aerosol is about 1/10 the concentration in the respiratory fluid of the total virus. So 1 in 10 or so are infectious. This black line here is at various viral loads, what's the cumulative percentage of secondary cases? Most of the cases are happening in this range of the viral load. The blue shaded line here is the same value as this, the ratio of infectious virions to viral load for my case where it's an exponent, where the viral load varies as an exponent. In this region where most of the infections are occurring, the model ratio of infectious virus in the aerosol to RNA copies in the fluid is 0.02 to 2. Same thing for the NF24, they're slightly different, but they're about the same. But if you look at just the respiratory fluid and you look at cell culture data, this is how much total virus they're finding, and this is the infectious virus. The infectious virus is 1 in 10,000. Okay? So in respiratory fluid, when you take respiratory samples and then culture them, they're finding the ratio of infectious to total virus to be 1 in 10,000. For our model to work, we need that ratio to be not 10 to the minus 4, but 0.02 to 2. In fact, more than 1. So there's some gap in our understanding here. There's a difference between what the cell culture data is telling us and what the model is telling us. So here's some possible explanations. One, we're putting out a lot more aerosol volume. If that's the case, then you put out a lot more infectious virions, this ratio will go down. The other possibility is that there's an enrichment of virus in aerosols. There's some experimental evidence for this. So that's another possibility. The other possibility is that the swab samples do not reflect what's going on in the aerosol. You could be generating aerosol at a different place compared to where the swab sample is measuring. And finally, it could be that in terms of how much infectious aerosol you need for a 50% probability of infection, that the aerosol dose, because it's delivered deeper and is lower. There's a number of factors that could explain it, but at this point in time, I would argue that there's a gap in our understanding in terms of how much infectious aerosol is, how much infectious virions is there compared to total virions in aerosol per milliliter of fluid. The model tells us it should be of the order of 0.01 to 1, 0.02 to 2, while the data tells us that it should be the order of 10 to the minus 4 or so. So there's this gap in our understanding that I think we have to resolve. So going on a little further now, keeping that in mind, if I look at the distribution, 120,000 events, 10,000 events a day, 12 days, 120,000 events, number of infections per event, 90% of events do not lead to any secondary cases. Combination of that occurring in low risk environments or low viral loads. That's not true that's averaged over the duration. But if you look at it as a function of time and look at when people, most of the infections are occurring after people are between when the index case is infected of 2 to 5 days in the infection. So most transmission is occurring 3 to 8 days post-infected. So the index case is getting infected, their viral load is building up. In that 3 to 8 day windows when they're infecting most people. But even in those time periods, about 70% of the index cases of the events are not leading to any infections. Viral loads in some cases are low. Not everybody builds up to a high viral load, or they're in environments that are not risky. In terms of if you now count it over the duration of the disease, 50% of the index cases do not infect anyone. The observational data suggests that this number should be more like 60 to 70%. So model's in the ballpark, but not right on. Okay. So I have this model that's a pseudo population model that captures various characteristics of the pandemic. It captures the characteristics that 20% of people are infecting 80% of the people. It captures how things are vary with this hazard parameter. So I have this kind of a pseudo version of the real world. And given that, I can now play these games where, okay, here's my ventilation. What if I put in a mitigation strategy where everywhere we improve the ventilation so that the air changes per hour is 6 air changes per hour? Or I put in a standard where the ventilation rate should be 10 liters per second per person. Or I put in a standard that say it should be whichever is better. Okay, so I did these 3 mitigation cases. So in my model, I have 6 cases. Each of them I reran with these mitigation cases. Okay. Here are my 6 cases. All of them are tuned to get an R of 3. That is, each case is infecting 3 people. These 3 are on the left are with the virions varying non-linearly with viral load. This is varying linearly. If you compare a cell here with the corresponding cell here, there's almost no difference. So I'm just going to talk about this. Okay. The air changes per hour, minimum 6 per hour, reduces the number of secondary cases by almost 50% if your model is well mixed. In the model where I consider some near field interactions, but high dilution of the near field, there's somewhat less because now there's some infections occurring in the near field, and that does not, the improvements in ventilation don't help as much as in a well-mixed model. And if the dilution rate is lower, you get an even smaller effect. So you can reduce this somewhere between from about 1.8 to 2.2 with this ventilation strategy. If, on the other hand, you specify it as 10 liters per second per person, you don't get as much. You get a little bit, but not as much as the. And if you take the better of the 2, you get something like this. So if you can improve ventilation to this extent everywhere, this is the kind of improvement you'll see. You still don't get down below 1. Okay, so significant impact. But it's sensitive. The extent of the impact is sensitive to how much the near field is being diluted. High dilution in the near field, you get a bigger impact because now the reduction in the far field is helping you more, less of an impact if it's not diluted as much. So we can kind of get some sense of how these mitigation strategies will work, given that our model captures these large-scale dynamics. Okay. So here are my conclusions. Is aerosol transmission consistent with it? I would say yes, we can reproduce this thing. But I think the big gap right now is understanding the virion content of respiratory aerosols. Are respiratory aerosols enriched in infectious virus compared to what we're finding in swabs using cell culture data, using cell cultures? So that's, I think, a big gap in our understanding right now. What controls transmission heterogeneity? It's the combination of this event parameter, event risk parameter, and the variability in viral loads that affect infection probability. And my third conclusion is, what are the implications? Ventilation improvement can significantly impact, can cut things by about a third or so, but extent depends on extent of near field interactions. Where do we go from here? This model, my base model is well mixed, but I have some near field enhancements. I've done some calculations using parameterizations derived from kind of CFD simulations, so I've kind of worked on that a little more. I think the big next step is to connect these to social contact models. In my model, I have a set of susceptible people that the index case is meeting, but in the real world, there's actually, you have various contacts. There are some people who you meet, like your family, you have constant contact with. Some people you have meet on a regular basis, like people you come to work with. Some people you meet rarely, like you go to a restaurant, go to a bar, those are random contacts. So kind of connecting what I've done here with the social contact model and then propagating infections and then evaluating consistency with epidemiological model, I think is a key step. And then of course, understanding how variants, because I've kind of relied on data from alpha and pre-alpha, what's happening with Omicron, impact of vaccination. It starts getting complicated because you have vaccination with variable uptake, you have waning immunity, you have much more complicated issues as you go forward in time through the pandemic. It's kind of in some sense easier early on when you can think of everybody as susceptible. So that's where I am, and I'm happy to take questions. Thank you very much.
All right, thank you, Prasad. We will switch over to Ido for our questions now. So if you have questions, please submit them. They will go through moderation, and then they will, pop up here. I can ask a question as someone who's a large-scale atmospheric dynamics person. The things I'm normally interested in are 10,000 kilometer scale. So, how well understood is this sort of micro scale mixing? I mean, I tried to follow along, but what sort of orders of magnitude, again, are you sort of looking at in terms of how these things mix around in an environment? I'm trying to get a picture of how certain that process is versus, anything else.
So, we're looking at indoor levels, indoor transmission, respiratory aerosols. It turns out, essentially think of it as a respiratory jet that you're putting out. It's kind of, there's room level turbulence. It depends on the flow patterns in the room, depends partly on ventilation, how things mix in the room. So it turns out that we've done some calculations. People have done CFD calculations for mixing in a room. And it turns out that if you do that, there's a variability in terms of concentrations in the room that probably span maybe an order of magnitude, maybe less. But then if you randomly distribute people in a room, so I've done this thing where rather than everybody in the room, in the well-mixed case, having one probability that people are breathing differently based on the output from the CFD model. Some people breathe in less, some people breathe in more. And in the end, the number of infections in that room comes out to be almost the same. So I've used a parameterization based on CFD calculations. None of the results change.
Interesting. Thanks. So we have a few Slido questions. First is from Helen. Do you know of work being done to measure aerosol virions versus swab? Yes.
There's one paper by Lednicki et al. In which they actually measured RNA copies in aerosols, infectious virions in aerosols, and also RNA copies in swabs. There's some work being done by Don Milton's group at University of Maryland, where they're measuring essentially RNA copies in swabs. They are then capturing respiratory aerosols from infected people. So that we're talking to them about trying to reconcile this incompatibility that we're seeing. There is some indication from their work that aerosols are enriched in virus, in RNA copies relative to respiratory fluid. And it has to do with the fact that the virus can behave hydrophobically. It can, the concentration of the surface layer of, say, of the respiratory fluid, say in your respiratory system, you could have it enriched in the surface layer. And if you have a film bursting mechanism, that aerosol will concentration of the aerosol will represent the surface concentration and not the bulk. So there is some indication there is in fact this enrichment in aerosols. In fact, we just were corresponding with Don Milton's group about that today.
Great question. Thanks, Helen. Peter Nell has a question. What about the Virion content of respiratory aerosols? Do you see a way ahead on that?
Yes. So there are people now who are capturing these respiratory aerosols, and it turns out that you have to capture it very gently. Otherwise, you could destroy you could take infectious virions and just break it up into RNA fragments. So you see a lot of RNA, but you won't correctly measure the virions. So there are people now, it's a collection issue, and people have started, Lednicki was the first to do that, and now people are starting to measure that.
Thanks for that question, Peter Nell. If you have any questions, please type them into Slido. We'll wait maybe another minute or so for questions to trickle in. Can I ask this is sort of a silly question. Those Skagit Valley super spreader events you showed early on, were those very, very early in the pandemic? Because I know Skagit was one of the sort of early kind of areas in Washington. Was that sort of the first few weeks of the pandemic, those events?
That was very early, yes, in the first few weeks, yeah. But there have now been a number of super spreading events that have been documented.
Do you know if how those events have changed over time? I mean, is it sort of, was that something that was more common in early COVID, or does it continue to be a problem?
It's hard to tell. We were talking about this today. I think there's clearly with Omicron and all, there's been quite a few super spreading events and stuff, but at the same time, you have less testing, you have more vaccination. So it's been more complicated, I think, to tease out that.
Helen's got one more question. Will you consider masks for a mitigation measure?
Yeah, so Helen, I've done these calculations where I do masks, and masks basically do two things. One is source control, and you can, but it also acts as a control in terms of how much you breathe in. And it turns out that the effect of masks is roughly linear. So let's say everybody in the room, with the index case and all the susceptible people, everyone wear masks with 50% efficiency. Okay? So the index case puts out 50% less. Of that 50%, each person is then breathing in 50% of what they would have breathed in. So you get essentially a 75% reduction in dose. And by and large, the reduction in infection probability is 75%. So it turns out that the response to masks is really linear. And of course, then it depends totally on what kind of mask people are wearing, and to what extent are they wearing them? Are they, for example, taking them out when they're talking or eating and stuff? And that's really what drives. But if we just assume people are masking for it, you really can cut down on mitigation. The problem is you don't see that very clearly in the epi data. And I think it's because we don't really know the sociology and the psychology, how people are wearing masks.
One more question from Peter Nellis. Well, what would you recommend for the way to approach the handling of this pandemic if we know what we know now, seeing also the different approaches of the different countries?
I think the first thing I would say is I think there's others who have made this point much better, that the early insistence that it was droplets and infected surfaces and not aerosols, and only a grudging acceptance of aerosols, I think really delayed a kind of response that then we got into a stage where it became political and stuff. I think if we early on had recognized that it was airborne, recognized that mass and ventilation works, I think it would have been a very different story. So I think going forward, for respiratory illnesses, we have to take seriously the notion that these are spread by, that respiratory aerosols are a major transmission mechanism, and therefore mitigating concentrations of respiratory aerosols in spaces, anything that does that, whether it's masking or ventilation, is an absolutely important thing to do early on.
I will give it maybe another 15 seconds and see if another question pops up. This has been a good question and answer session for a virtual talk. Thanks everyone who's been submitting them. Okay, let's say that we're wrapping up. It's always difficult to tell, and please join me in thanking Prasad for taking time today to tell us about this important topic. Thanks, Prasad.
Thank you so much.